Aloha, my friends! Welcome back to another lesson. Last we left off, we clarified Newton's third law and understood what the normal force was. Today we're going to be continuing on that sort of concept and we'll talk about friction. So let's take a regular block, for example, that's resting on the ground, and let's talk about what forces would be acting on that block. So, we know there's going to be a weight force imposed by the Earth and its gravitational field, so I'll draw that in as weight, which is just equal to the mass of the block times the gravity. We also know there's going to be a normal force because the surface is going to be pushing back up on the block in the y direction. So I can go ahead and draw that in. And in this case, because we don't have a slope or anything irregular, we know that the normal force is just going to be equal to the weight force. Now let's say we push the block on this surface and we gave it some force towards the right, and we'll just call that F for now. How would we expect this block to behave? Well, intuitively we know that if this block is pushed, we know that the block would accelerate at first, but then during the course of time it would start to slow down. Which means there must be a force counteracting the block's motion. Otherwise this block would just continue to move forever. And this counteracting force is known as the frictional force. And I'll put that in as well. And it occurs due to two surfaces rubbing together. So that's FFR, and that's our frictional force. So I'll write that down just so you have it on record. And there are two main things I think that you need to keep in mind when we talk about frictional force. Number one is that the frictional force always acts parallel to the surfaces, and it acts in the direction that opposes relative motion. So I'll put those 2 points on screen as well, right next to us. So let's go back to our diagram here. If we zoom into the surfaces, we see that there's little peaks and troughs that are in contact with each other. So I'll put that in. So if I was to zoom into this surface, I know that the surface of the box would be interacting with the surface of the ground, and there'd be little peaks and troughs at the microscopic level that would have multiple points of contact with each other. And the closer we bring these surfaces together, the more points of contact we would have, such that the magnitude of the frictional force would be greater. And the way we can bring those surfaces closer is either by providing a greater force from the top, or by increasing the weight of the object, both of which can be counteracted by an equal normal force. So from this we can see that if we increase the normal force, we'd experience a greater frictional force. And I can write that down as saying the F of Fr, which is friction, is going to be proportional to the normal force. But the normal force is not the only factor that determines the magnitude of the frictional force. We also need to take into consideration the surface roughness of the materials. So, surface roughness is also written as mu, which is also called the coefficient of friction. So I'll put that down, coefficient of friction. And it's unique to the materials that are interacting with each other to give us that frictional force. And this is also referred to as the surface roughness of the materials. So the smoother the surface is, the lower the coefficient of friction. And we would expect the coefficient of friction of ice to be far less than something like, say, concrete. Taking both the normal force and the coefficient of friction into consideration, we can come up with an equation for frictional force. And that equation ends up becoming F of Fr, which is our frictional force, is equal to mu, which is our coefficient of friction, multiplied by our normal force. Now, friction can be broken down further into two types, being static friction and kinetic friction. Where static friction opposes the initiation of movement by being equal and opposite to the applied force. So if I was to go back up to our diagram, The frictional force here, F of Fr, would be equal to F, such that the box would not move, and the static frictional force would continue to oppose the applied force until this applied force was greater than the frictional force. Kinetic friction, on the other hand, would oppose the motion of the moving object once that object has already overcome this static frictional force and is in movement, or is experiencing movement rather. Now just go on ahead and put in the frictional force and the direction of the frictional force, but how would we determine it otherwise? Well, if we apply a force towards the right, we'd expect the block to also move toward the right. And if we look at our definition of friction from before, we know that friction acts parallel to the surface and acts in the direction opposing relative motion. So we can say that if I was observing the block from the ground, it would be moving towards the right away from me. So we can say, because the block is moving away towards the right relative to the ground, we can say the friction would be acting in the opposite direction, which is towards the left. Now there's a common misconception that friction only acts in the opposite direction of motion. However, that's not always the case. And to demonstrate that, I'll use another example. So let's say we have a block, and we'll call that block B, and we have another block, block A, sitting on top of block B. And let's say we apply a force towards block B, and we'll call that F. What do we think will be the direction of the frictional force acting on B and then acting on A? For now, let's simplify the problem a little, and let's say that the surface block B is sitting on is smooth. So we can neglect the effects of friction between block B and the surface that it's sitting on. So since we're applying a force onto block B, there will be a tendency for block B to move in the direction of the force, which is towards the right. And as a result, there will be some form of friction occurring due to slipping and sliding occurring between block A and block B. Using the same logic as earlier, to find the direction of the frictional force acting on block B by block A, we'll have to start by standing on block A. So let me draw a little person here. So if we look at the relative motion of block B in comparison to block A, we can see that from block A, that block B would be moving away from us towards the right. And if we scroll up, we can see that the frictional force acts in the direction opposing relative motion. Therefore, the frictional force acting on block B, imposed by the slipping caused by block A, would be towards the left, because the block B would be moving right relative to block A. And I can write that in as a vector, so I can say F of Fr experienced by B is towards the left. Now what about the friction acting on block A as a result of the slip and slide occurring between A and B? Well, let's just repeat the same sort of procedure. So let's say we're standing at B, and if we're standing at B, we see that A is actually moving away from us. So the relative motion of A is towards the left direction. Therefore, there must be a frictional force acting in the opposite direction, which will be towards the right. And if I draw that in, the frictional force will be towards the right, F of Fr experienced by A. And what you'll find is that this is actually in line with Newton's third law as well, which states that if an object, which we'll call object A, exerts a force on object B, then object B will exert a force of equal magnitude and opposite direction back on object A. So we know that these two, although in opposite directions, will be of the same magnitude. And this makes sense intuitively as well, because we wouldn't expect block A to accelerate in the opposite direction to the motion of block B. In fact, it's this frictional force that acts on block A that keeps this block in motion. This brings us to the close of this lesson. I hope it clarified the concept of friction a bit further, and as always, thank you for joining me. I'll catch you at the next one.